Μπορώ να μιλήσω. Ναι, τώρα ακούμε. Ξεκινάμε το συζήτημα και μετά. Κάντε ένα check να ακούνε, θα απαντήσουμε.
Can you listen to me?
From Spontanea.
Hello?
Yes, I can. So you can start the season 2.
Good morning, everybody. Gomon, Sweden, Dobrodan, Croatia, and Buongiorno, Italy, and Kalimera from Strathclyde. I am John Kokarakis from Robert, and I will teach you the second session, which has to do with the design of LNG fueled vessels. The first slide of the presentation depicts a Type C gas storage tank, which is considered to be the most critical aspect of the fuel system in an LNG fueled vessel. So a large part of our presentation will be devoted to such type of storage tanks. The general knowledge areas that you need to deal with are described herewith. First of all, in the design, we need to determine the functional requirements. We need to ensure that the safety of the system is at least equivalent to the heavy fuel oil-fueled ships. A necessary ingredient of the study is a risk assessment. By risk assessment, we mean the identification of hazards associated with the installation and possibly the mitigation, the measures that we need to take to mitigate this type of hazard. It's a necessary ingredient. For example, the fuel tank, storage tank, where we store the LNG in liquid form, actually in a saturated form because there is a combination of vapors and liquid phase, has to be sufficiently protected against damage, mechanical or otherwise, from adjacent fire or from collision, grounding, so it needs to be protected. And a scenario has to be devised that will tell us what will happen in such an eventuality. The fuel containment systems and the piping must be so arranged that the potential release of gas will not cause problems, and the release of the gas will be in safe locations. Also, what remains after an accident from the propulsion standpoint has to be enough to provide capability for maneuvering and powering. So the tank design process is governed, which is the most critical aspect of the system, by what we call the 4 Ds. First of all, define the operation requirements and possible restrictions. The second is the determination of the design loads. The third, the determination of what rules are applicable and what standards. And last but not least, the design of the tank structure and its supporting arrangement. So operation requirements and restrictions have to do with the definition of maximum and minimum pressure and temperature ranges, determination of the storage volume. How do we determine that? If we know the range of action for the ship and the fuel consumption in the engines, we can determine the necessary quantity of gas. Knowing the density at that pressure and temperature, we can compute the necessary volume. We need to determine the LNG consumption rate and the worst possible environmental loads for the design. The LNG has to be safely stored and has to have high reliability and a specified fatigue life. The fatigue life, as you realize, for such an expensive piece of equipment, has to be more than the design life of the vessel. So assuming that we are dealing with a 25-year-old, 25-year life, it has to be at least more than 25 years. We need to determine the inspection schedule for the tank, at least for the parts of it that can be inspected, because some parts, as we're going to see, are not possible to be inspected. We need to determine the bunkering requirements, which are very important, and optimize the space that the tank will be, as well as we need to determine the interface with the rest of the systems aboard the vessel. Design loads. I will go quickly through the design loads definition. Besides the weight of the fuel in the tank, we need to have to consider the inertial loads, the mass of the fuel times the acceleration. We have three components of acceleration in the longitudinal direction, transverse, and vertical direction. This can be determined either by semi-empirical formulas or by sea-keeping computation. If we utilize the wave spectra, these are the 10 to the minus 8 probability accelerations. So the objective is to determine the triaxial acceleration and the center of gravity of the tank, which will act along with the vector g, who refers to the static value. Another important quantity is the sloshing. The sloshing loads, which depend on the geometry of the tank, on the filling level, and the fluid density, as all the pressures depend, and the orientation of the tank. The tank can be horizontal or even vertical, under certain limitations. We utilize baffle plates to limit the movement of the fluid inside the tank, and we try to avoid resonance. So what we do, we compute the natural frequencies of, say we are looking sloshing in pitch, we compute the natural frequency of pitch, and then we try to avoid to fill the tank in such a way that we have resonance with the value that you see mentioned here for a cylindrical tank. This is a poor man's check of resonance, because of course there are more advanced CFD calculations that will do a much better job. If you do it with a poor man's method, with this simple formula, then because of the computational uncertainty, we try to go outside the plus or minus 20% band. So we take 0.8 of that and 1.2 of that value, and we are out of that range. Of course, we also have possibility of water on deck. If it's on the deck, we have green water, slamming. It remains to, you have to devise a nice method, like a Karman wedge analogy, experimental work, or CFD, to compute the wave forces on the tank due to green water. In addition, because many tanks are constructed with vacuum inside, the pressure behind the wall of the tank is zero because of the vacuum, they are subject to external pressure, compression. So that means that we need to consider a buckling possibility and do a buckling check. Further to that, we need to check against accidental loads like grounding and collision. Grounding is about 1/3 for accidents in general for ships. Because of the collision problem as well, we subject the tank to a half a G deceleration in the forward direction and a quarter G deceleration in the aft direction. In addition to that, for some types of tanks that we're going to see, we might have an upward force due to buoyancy. In case of flooding, in case of an accident, water will go in and will push the tank up. Further to that, if we have fire in adjacent space, we might see a pressure rise, which might be considered by considering pressure rise by 20%. So we consider pressure 120% of the maximum allowable relief valve setting and check the strength of the tank. In general, we try to separate hazardous areas from non-hazardous ones. One way of separation, of course, is the fire insulation. We use A60, A0. By A60, A0, we mean special classes of insulation. A60 can withstand fire for 60 minutes. In addition to that, bulkheads surrounding the hazardous area can have cofferdams, empty space which has air insulation. The build systems from dangerous areas, from hazardous areas, should be separate from those of gas-safe areas. And we'll see how we classify the hazardous, various degrees of risk, of safety risks around the vessel. The ducting also that is used for ventilation of hazardous areas should be separate from the ducting of that for gas-safe spaces. I put these pictures here. These represent my first job in professional life. There was a semi-submersible off the coast of Aberdeen, which where the design of the flare system was not so successful. This was the burner. The fluid from the well went out and compressed air was used for atomization to achieve a better combustion. Unfortunately, because of the design, look at this, circular design, in the past they had to unscrew this and introduced inferior metallurgical properties, untempered martensite, which caused cracking of this part, and then we had communication of the well fluid to the compressed air system of the ship. The two were mixed and methane found its way to the pump room, which is a traditionally gas-safe area for this type of vessels. 2 people died because of this mixing. So segregation, hazardous, non-hazardous, separate systems, no matter what the cost is. The location of the tank is determined by, is going to be established by the International Gas as Fuel and other low flash point fuels, IGF code, which will come hopefully into force the first half of 2017. In the code, there is still the most critical aspect is where to put the gas storage tank. There is what we call the deterministic idea, where we put it for cargo vessels at a distance of B/5, 1/5 of the breadth, or 11.5 meters, whichever is less. And then for passenger vessels, this goes up to, goes below, is more strict, to B/10. For the tanks that are close to the bottom, the distance is B/15 or 2 meters, whichever is less. For tanks in the bottom, yes?
Sure. Excuse me. Can I see the previous? As far as I know, the idea of this regulation is still under discussion. Is it confirmed?
No, it has been finalized.
Finalized.
Yes. Last year it was finalized. But this issue is still under discussion because, as I will show you, there is also another idea came from Norway.
Yes, but still under discussion.
I would say that is what it looks like is that both schools of thought will be applied. So what I show you here is the deterministic, which is actually very simple, and then I will show you also the what we call probabilistic school of thought. So this is simple. You know where the distances are. You put the tank there, B over 5 or B over 15 for the bottom, because we also like to put tanks underneath, under the main deck. And we probably have grounding, so we want to avoid that. So the B over 15, if you remember, compare that with the double bottom height. So the other school of thought, to reply to your colleague, is the so-called probabilistic approach initiated by France and Norway, where we try to achieve certain value for an index, FCN index, which is on the basis of location of the tank in the checking in the transverse, vertical and longitudinal direction. What do we mean by that? In the longitudinal direction, if you are forward, you are in trouble. In the transverse direction, if you are close to the side cell, you are in trouble. In the vertical, if you are close to the bottom, same. So depending on where the tank boundaries are, we have certain values associated with that index. These values can be found in the probabilistic stability. So those of you that deal with this, you can find these values through probabilistic stability ideas. And the value has to be 0.02 for passenger vessels, that's stricter. For cargo vessels, 0.04. To reply to the question, it appears at this point that both are acceptable. We will know better when the code will come into force, most likely July of 2017 by IMO. So discussing about a tank below deck, below accommodation, usually people don't like to put pressurized containers because of the amount of energy below accommodation. So there is a limitation. The pressure in the tank has to be less than 10 bars. 1 atmospheric pressure is 1 bar. So we don't want to have more than 10 bar gauge in the tank. The tank has to be ventilated, has to be ample ventilation in the space, usually minimum of 30 air changes per hour, and it has to be isolated from adjacent space. Like you see, the storage tank goes to feed the gas engine with piping which has double wall piping. At the same time, there is A60 class fire insulation and the cofferdam. Usually both of these measures are necessary, but we can get away without the cofferdam in case of Type C tanks. Type C tanks are considered to be, as I will show you, a little bit safer than the others, more difficult to leak or have problems. For example, you see some arrangements where the storage tank is below deck. This is acceptable. As we realize, the space is a premium in the vessel. The safety analysis that we do aims to reduce the probability of leakage. In case of leakage, we try to reduce the probability of ignition by removing potential sources of ignition, like sparks, for example. We need sparkless fans, and also to reduce the consequences of possible release and explosion. Now, the types of tanks. Yesterday you discussed the membrane type of tanks promulgated by the French company GTT. And you discussed the advantages and the disadvantages of this tank. Today we'll discuss the remaining types, type A, which are not participating. I'll show you pictures. They do not participate in the global strength, in the hull girder strength of the vessel. They are part of the ship, but you don't consider these tanks to be part of the longitudinal strength of the vessel. And they are not essential. Suppose we lose that tank. They are not essential to maintain strength and integrity. Type B are designed with advanced analytical tools and methods, and we compute the stresses, the fatigue life, we'll discuss a little bit about it, and possible crack propagation. Crack propagation ideas are applied in the design of type B tanks. Then the cylindrical tanks I showed before are the type C, or I will call them cryogenic, from the Greek word cryo, means cold, cryogenic pressure vessels. They are designed on the basis of recognized codes, and they are supplemented by IMO, IGC, and IGF codes. What do I mean by basis of recognized codes? One example, I will show you a series of these regulations and codes. One of them is the ASME, American Society of Mechanical Engineers, boiler and pressure vessel code, or the British standard BS 5500. And they have been used for decades on onshore applications. We do not see why not to be used in on board vessels. What is the main hazard? The main hazard that we have is leakage and leakage of LNG on the vessel and touching the steel structure of the ship. As you know, as the temperature is reduced, the steel loses its ductility. If we lose the ductility, the steel will become brittler and brittler and brittler, and that means that it's very easy to crack. The steel will become like glass. Glass is very strong but very brittle. This is what will happen if we have LNG spilled on deck. We'll see like a branch of cracks to be formed. And cracks, as you realize, are not good to have on the main deck. So this is the major hazard. Type A and Type B tanks are atmospheric tanks. The pressure is very low, below 1 bar, and they are subject to boil off. Of course, Type C are also subject to boil off. What do we mean by boil off? To have liquid LNG, we need minus 163 at pressure closer to atmospheric. But outside we have 20, 25, maybe 15 in Scotland. So what are you going to do? There is inevitably, there is heat transfer, no matter what the insulation, there is heat transfer from outside, from the surroundings. So some gas will vaporize and go out. So we lose some fuel. Type C tanks are a little bit better because we have increased pressure, 5, 6, 7, 8 bars. And in this, if you look at the graphs, say methane, primarily we have methane. If you look at the graphs at increased pressure, methane is liquid at higher temperature, not minus 163, maybe minus 100, minus 50, which is easier to keep than minus 163. So type C tanks can reduce the boil off, can keep the fuel in an easier way. And of course, because of that, they have lower maintenance cost. But what is the disadvantage? I will agree with yesterday's speaker that the space utilization of type C tanks is poorer. So if we can, in the tanks, if we have some failure that cannot be detected, will not be able to detect in the future inspections, we need to ensure that this critical state that will occur will not be degraded to failure for the lifetime of the tank. So if we have a crack, we need to ensure that this defect, we assume that the weld will have an initial defect, and this defect will not propagate to a critical size. That crack will not get critical size for the lifetime of the tank. What do I mean by critical size in a crack? After a crack grows, it reaches a certain point where it propagates with the speed of sound in steel. So this is the critical condition, is uncontrolled brittle fracture. So we need to ensure that for the lifetime of the tank, areas that cannot be inspected will have no propagation to critical size. For type C tanks, because the probability of structural failure and leakage is lower, we do not require to have a redundant barrier, as we call a secondary barrier. For others, besides the first barrier to LNG, we have also a secondary. For type A tanks, for example, we have the hull itself to play the role of secondary barrier. For type B tanks, we have partial secondary barrier. All we need is to collect the leaked gas. For type C, we do not need, no need for a secondary barrier. Although most of the type C tanks are made by an inner and an outer shell, a very expensive construction, which we have practically a primary barrier and a secondary barrier. But it is not necessary. We might have a single cell tank. So the four types of LNG tanks are shown here. This is a spherical type B tank. This is a type A tank, and this is a type C tank. This is the membrane tank that you saw yesterday, which we find in LNG carriers. But it can be utilized in as a tank, a fuel tank in LNG fueled vessels. The GTT had the idea to consider retrofitting of ships by jumbo-sizing, increasing the length, by adding a section and converting it to a membrane tank, of course with appropriate cofferdams forward and aft of the tank. So the membrane tank is an idea of GTT and can be utilized to save space. Imagine if you have, for a tanker it's not difficult to add a C-type tank. But what is going to happen in a bulk carrier? In a bulk carrier you have the cranes, you have the hatch covers, where are you going to put it? Well, here is the answer. If you want to use LNG as fuel, you can put it by adding a section and use a membrane tank. Further to that, suppose you have a container ship. You can have a container contained tank. You have a, I would say, a 40-feet container, and inside the container, the standard FEU, 40 equivalent unit, you can have a fuel tank, and you can have few of these contributing and going to the engine. So that's another possibility. Looking at type A tanks, we have water ballast tanks, we have the secondary barrier, which is the surrounding hull. This is the secondary barrier, and of course the primary barrier. Between the secondary barrier and the primary barrier, there is insulation. We need the insulation to keep the temperature to minus 163 degrees. Here's a picture. Anybody knows what is this brown color? This is insulation. It is not steel. We put insulation around. So from what we see here, from the picture here, it must be foam insulation. Foam can be applied very fast, not as effective as other types of insulation, but this appears to be foam insulation. This is a part which is weighted to be insulated. So we can use perlite or foam. Type B are also known as Kvarner MoS tanks, and they are spherical. They require a lot of space, as you can realize, but the first of this type of vessels as carriers have been utilized, have been done in Japan. We might see tanks, spherical tanks as well, which can be also prismatic. What is the difference between tank B and tank A type? Very minor difference. It depends on the way that we study it. In tank B, we'll discuss, we apply what we call leak before break. So this table indicates the major differences because various types. And let's look at this leak before break philosophy. When we have a crack in a vessel, this crack will propagate in the, let's assume that this is like a circumferential crack, which is subject to longitudinal stress. Always the crack is propagating perpendicular to the principal stress, although in a cylindrical vessel, the maximum stress usually is in the tangential direction, is called the hoop stress. But in the longitudinal direction, you might have a combination of the longitudinal stress from pressure and bending stress. We also have bending. So let's assume for the moment of this discussion that we have a longitudinal stress driving the crack. So the crack is propagating circumferentially. But at the same time, the crack is propagating through the thickness. So we have 3 degrees of freedom. Going that way, going the other way, clockwise, counterclockwise, and through the thickness. We want to have the crack become critical only through the thickness. We don't want the crack to become critical in the circumferential direction, because if we do have that, then we have a problem of shattering the tank within not seconds, fractions of a second. Speed of sound in the steel is 4,000 meters per second. So going back to fracture mechanics, you don't need to know fracture mechanics to apply this idea though. The crack will become critical when the stress intensity factor of this crack will become equal to the fracture toughness of the material in the circumferential direction. So we have this scary looking formula, but don't worry, no need to worry about this. MK is taken, is a Kobayashi magnification factor. You take it from this graph on the basis of the dimension of the aspect ratio of the crack, and then you can compute the pressure which will make that crack to run critical. At the same time, we apply the same idea to find when the through thickness propagation will become critical. We get pressure for the circumferential, critical pressure for the through thickness. To have this occurring first, this pressure has to be larger than this one. So eventually, we end up with this formula, which will give us a condition which, if satisfied, we are not going to have critical crack propagation. What we are going to see, the crack will go through the thickness, we are going to see leak. We know when we have leak. How do we know? We know because we are going to have gas detectors in the interbarrier space. Interbarrier space is the space between primary and secondary barriers. So the detectors will come off. We know that something is going on. So the leakage, which has to be contained for 15 days, will be known. So we can take care of it. The problem that we know is easier to tackle than the problem we don't know. So this condition will tell us if an initial defect, an initial crack, will become critical. The thickness is implicitly contained in the Kobayashi factor. But the leak before break, you can learn more about it, is a basic design criterion, is in the design of pressure vessels. So type A tank, which actually does not have leak before break ideas in its design, has relatively low pressure, as we said, and it is what we call independent tank. In the membrane tanks that you saw yesterday, there is insulation around the tank. Here, we have supports, but it is what we call independent tank. It is not integrated with the hull. So, to be independent, it has to be supported. The support system is, we have supports to prevent rolling, supports to support the weight of the tank, vertical support. We have supports to prevent pitching, longitudinal motion. And we also have supports, I don't know if you can see here, supports to prevent lifting of the tank. I believe this is also applied in type B tanks. This type of supports we also have in type B. Somebody might decide that they like to have type A or type B tank, not type C or membrane. This is also an option which must be put into the table. Here you see a picture of independent tank A and a series of what we call anti-floating devices. So in case we have flooding and we have an empty tank, buoyancy might push it up. We don't want that to happen. So this will keep the tank from lifting up. But these supports create problems, meaning that they have these supports need to be checked for cracking, and their design needs to be evaluated. In type C tanks, which are mostly double walls and vacuum insulated, we have two tanks, one inside the other, the inner tank and the outer tank. The space between the two, right here, is filled with insulation material or and kept under vacuum. But in addition to that, we have reflection shields for radiation. If you go back to your heat transfer courses, take two plates, put one plate in between, which acts as a shield. You will notice that there is a reduction of the heat transferred from one plate to another. Now we try to avoid heat transfer from the outer level to the inner level. So we try with radiation shields, not one, not two, maybe three or four. We try to reduce this heat transfer. This tank has to have what we call a high holding time. Holding time is how long the tank can withstand and keep the liquid inside. Usually type C tanks have very high, the double wall, very high holding type, and they have excellent insulation properties, but they are expensive. Not as expensive though as the membrane tanks. Membrane tanks you discussed yesterday. I'm not going to spend time on that. Do you know which type of tank containment system we have here? I can tell you there is corrugated
MK3.
Mark III, yes. We have a Mark C system. I remember Mark III. The trick is Mark corrugated, the two R's. Corrugated Mark. It's not easy to remember. The other is NO96, and now there is Mark V, and so on. They increase the thickness of the insulation, trying to get lower boil-off rates. Because boil-off is not good. Why is not good? We lose fuel, number one. Number two, methane cannot go. If it's not burnt in the engine or somewhere else, or reliquefied, it is not a very good idea to have methane in the atmosphere. It is 20-25 times more damaging to the environment than CO2. We don't want methane emitted freely in the atmosphere. So overall, the system, the fuel system, we'll discuss a little bit about fuel systems. We have like the bunkering facility going to the fuel storage, fuel containment tank. Then we have some treatment. What do we mean by treatment? We vaporize it. We would like to vaporize. So we utilize heat exchangers. And to send the gas to the engine, we need to compress it. So we have vaporization and compression. Then we have a central, a master valve, as we call it, which in case of leakage, we close it and we isolate the source fuel from the tank. And then we have what we call a gas valve unit. The gas valve unit, among other things, it has a redundant isolating valve, which I will show you later, is a block and bleed valve arrangement. Also isolates. Then we have the engine, dual fuel, and then we go to the propeller for propulsion. So this is a schematic view of the fuel system. But in reality, it is a few, maybe 100 meters of drawings. Associated with the LNG fuel vessels are two types, two different philosophies of engine rooms. Two different types. We have what we call gas-safe engine room. As the name implies, there is no release of LNG, cannot be release of LNG in that room. We design it in such a way that LNG cannot leak. How? I will show you. And then there is the emergency shutdown. In the emergency shutdown philosophy, we can have release of LNG. We don't like it, we try to avoid it, but we might have release of LNG. So to take care of that, because we cannot lose power, we need to have a redundant means of propulsion. So not only one engine, but we need to have two engines. We lose one engine, we utilize the other. So we can go to our origin, to our place of destination. So the gas safe. The gas safe, notice that after the gas valve unit, or actually before, after the master valve, we have double pipe. I will show you the double pipe. There is inner and outer. Very expensive. This is very expensive pipe. And then goes to the engine. And because of this double pipe and arrangement, because of the ventilation, we believe that this is a gas-safe space. No gas there. What does it mean for you, the designer? It means that you can utilize electrical equipment that it is not explosion-proof, according to IEC, International Electrical Code. If you are in a gas hazardous area, there are special regulations that are required for equipment like pumps, fans. They need to be specially designed. And that means they're expensive. So in the gas-safe engine room, this is not required because we believe that we've done our job properly and there is no way that this gas will be released. You will see though that the double piping is very complicated. I will show you some pictures from MAN and it is not easy to make. So this is one way. After the master valve and before the engine, we have this gas valve unit where we have the block and bleed valve. It's a three valves. This one, and this one is bleeding, venting to the atmosphere in this case. And this is an additional isolation. This is the gas valve unit room. The emergency shutdown engine room. Here we don't have double pipe, expensive double pipe. We have gas detectors which look like this. And in this case, because there is a possibility to have a likelihood to have gas release, all the equipment must be explosion critical equipment like fire and gas detectors, fire and gas alarms, lighting, ventilation fans. They have to be explosion proof, expensive explosion proof. Also the ventilation must be 30 air changes per hour. This is a universal value, appears to be the norm for ventilation. And what you see in this picture will be reproduced adjacent to it because of the need for redundancy. Please keep in mind that this engine room, because it's gas hazardous, has to have A60 insulation, class A60. I'll show you how it looks, this A60 class, and possibility of cofferdams. Yes, please.
Regarding catholic machinery space, the IJET code covers the double wall pipe system, but it's not covers engine itself. So, in the classification point of view, how do you assess the safety of the? You are just discussing the manufacturer.
It covers, and it is part of this presentation, it covers the connection of the double pipe and the valving and the injection area. There is a special valve in the engine that regulates the mixing, as Professor Theotokatos described. It regulates how is this mixed and how is it to be isolated. This is the only part we cover. The rest of it is
have you gas leakage?
There is no, so far there are no incidents of problems. Of course, there are about, as you probably know, there are about less than 100 ships that are LNG fueled. So the makers so far are doing a study to improve the safety of their engines by utilizing proper designs. I refer you to the Wärtsilä and MAN literature, where it say how to avoid communication between, say, lube oil with gas, and what we discussed before, the lack of segregation between hazardous and non-hazardous spaces in the engine. But we are concerned only until the valving, where the mixing is taking place. Now, as we discussed, since 2009, we have started the development of the IGF code, which will include other gases besides LNG as well. LNG is not the only fuel available. We might have also, for example, methanol. Methanol is not cryogenic, and but it is actually low flash point and might be utilized in the future. So it's a low flash point gas and toxic. The rules related to the use of methanol are going to be contained in the IGF code. It is not applicable. The IGF code refers strictly to ships that use LNG as fuel. The ships that carry LNG as cargo, LNG carriers, LPG carriers, are governed by the IGC code, as you probably already heard so far in this series of lectures. So I would like to show you some ideas for the tank. Like, we have the main tank, double wall tank as it looks like, and the space in front of the tank is called tank containment or tank connection space. This space is very important. It's also called the cold box. In this space, we have a series of equipment like heat exchangers, pumps, that take the liquid, take the LNG, and they send it to the processing unit where it vaporizes and compressed to go to the engine. Because we might see leakage in that space, and the rest of the space here might be contaminated by gas, what we have, this space is communicating with the outside with what we call an airlock. Airlock is a room which is just air pressurized above the surrounding space, over-pressurized, and presumably is free of gas. It has two doors, and one door is closed, the other is open, and this is how we communicate. I will show you more about how airlocks are required to be according to the IGF code. But the airlock is a very efficient means to communicate between hazardous and non-hazardous space. Leonida, why doesn't
I'd like to make a break now because it's 3:30 to ask for any questions. We have 2 or 3 minutes in order to ask if there is any question. Fine. In order to have the break, and we can continue afterwards. Yes. So
we stop here.
Yeah.
Location of spaces.
Yeah.
And we'll have some time for questions. I can find.
And also questions from the distance learning, from Spontanea, if there is any.
My Russian friend.
If there is any, we can see it here.
Okay. So, questions from the audience. We had some questions during the discussions, but overall, what is your feeling? You realize LNG is an explosive gas. If we have between 5 and 15% concentration of LNG, we have explosion. So we need to regulate. But I would like to tell you that the safety record of LNG is actually fantastic. We have very, very few accidents. We have many more. And there are oil tanker, chemical tanker cousins than LNG carriers. LNG carriers are very, very safe. And we believe the same safety record can be achieved in LNG ships. In your opinion, what is more dangerous, LNG or LPG? Please.
I think that LPG is more dangerous because
you are absolutely right.
As far as I've read, LPG has further problems than LNG. For example, it's prone to bleed if it's heated from underneath, causing an explosion and just penetrating through the tank and so on.
And the most critical one is that LPG is heavier than air. LNG is lighter than air. So suppose that we have like LNG spilled in the water. We don't have expensive cleaning like in the case of heavy fuel. LNG will evaporate, will go up in the atmosphere. Of course, it's going to do the damage to global warming, but nothing will remain. LPG is heavier. So somebody might be, who knows, might be smoking around, and then we have problems.
We have also the contribution from Slovenia. Mr. Andrea has answered also to your questions.
Very good, Andrea. From Italy. Molto bene. So I presume, one more.
Yeah, I think the safety issue of LNG is not just simply to say the historical record guarantee that LNG is safe, because this is the LNG fuel vessel. We have to apply very different arrangements, especially for using two-stroke engine, like BMW. There is the fuel pressure goes up to 300 bar. So for conventional LNG carriers, the fuel supply system would be installed the upper deck, but in some cases for the commercial other types vessels, the system would be installed below deck. So what if there is a kind of high concentration of LNG which takes place in explosion? So that seriously affected the stability of construction setup. I think we have to approach these methods more likely to the arrangement, how we arrange the system more safely, not the energy property.
The key here is the pressure. And I believe there are makers right now that have come up with dual fuel engines that are not necessarily high pressure. There are also two-stroke engines of low pressure. 300 bars are primarily from MAN. It appears that there are also other designs that have utilized lower pressures. So high pressure means higher risk. For the same volume, the energy is much more. But I believe that gas engines are not a key safety issue. In my opinion, the key safety problem lies with the storage. I'm more inclined to believe that it's easier to convert even an existing engine even an existing heavy fuel oil engine can be converted to dual fuel. My problem is not so much the engine as it is the fuel system itself, and I will show you what happens after the tank. You need to keep the pressure high, to build up the pressure by using heat exchangers, by pumping the additional amount out, and processing, as we call it, in the fuel, in the tank connection space, in the cold box. This is really the most critical aspect, and this is why the tank, I don't know if you know, but an LNG as fuel addition is about, the cost is about 20% or more of the cost of the ship. 20% is a lot. And most of this cost goes to the tank. It's not so much the engine. I have been asked by a banker, what is the main, he will also believe that the engines are the critical. It is not the engines, it is the storage space and the associated equipment with the tank, which we will see. I mean, it's like not only the tank. So hopefully we'll have enough time after lunch. I don't want to take more of your lunch time. I hope you learned a few things, and we'll continue after lunch. So thank you for your attention. Manoli, we go to...
Καλά.